to get started. Thank you. Yeah, I will look at the practice missions at the end of class. Okay, guys. So once it gets to be about like 3:25, let me know. All right. So anyway, I'll begin with a word of prayer. Dear Father, we thank you for your many blessings, and thank you for this day. Just ask that you'd guide our steps, help us to understand a little bit more about eigenvectors, and just help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so thank you for your work up here. Let us talk about eigenvectors and their theory and all that again. Let's try to work some out. So I showed you last time a bit, we defined eigenvector and eigenvalue, right? But I'm going to do a little bit more this time. So if T is a linear transformation from Rn to Rn, and beta is a basis for Rn, then we proved that the matrix of T with respect to the beta basis, right, was equal to beta inverse the standard matrix of T times the basis matrix of beta again, right? Where, just to be clear, if beta is V1 through Vn, right, this is an ordered list of vectors, that's what a basis is, then our notation brackets of beta is an n by n matrix formed by gluing together these n vectors to an n by n matrix, right? And that has to be an invertible matrix because the basis is assumed to be linearly independent, right? So we take the determinant of beta, it's non-zero, it's a linearly independent, it's an invertible matrix. And this thing I just wrote, can you guys tell me what this is called? I don't know if I've ever said this in here, but what this means, like generically speaking, if you have that B is equal to like P inverse AP, then A is similar to B. That's similar. This marker is dead to me. So these are similar matrices, like the standard matrix and the matrix with respect to beta. These are similar matrices. Notice that the determinant of similar matrices, right, is what? It's not just similar. What is it? It's the same. So if we take the determinant P inverse AP, that's the determinant of P inverse, P inverse A, because what property am I using, guys? We have that the determinant of A times B is equal to the determinant of B times, fine, let me be less weird. We'll just do determinant of P inverse times the determinant of A times the determinant of P, right? This is just the determinant of the product is a product of the determinants, but notice that these two guys be canceling, right? And we just get the determinant of A. So like the determinant of two similar matrices are equal. So what this means then is that the determinant of the matrix of T with respect to the beta basis, right, is equal to the determinant of the standard matrix of T, right? Agree? So what does this mean? Well, what this means is we can define a new thing. We can define the determinant of a linear transformation. How should we define the determinant of a linear transformation on Rn? I mean, we could define it to be simply the determinant of the standard matrix of T. right? But what does the calculation right above show you? You could just as well calculate the determinant with respect to any choice of basis. You get the same thing, right? And that's why this is a natural definition. Yep. Oh, okay. Now, so furthermore, definition, if T is a linear transformation from Rn to Rn, and V not equals to 0 has T of V equals to lambda V for some lambda in the reals, then V is an eigenvector with eigenvalue lambda for T. Notice that we have T, we could write T of V minus lambda V equals to 0, which we could trade for T minus lambda times the identity map acting on V equals to 0. All right. Now, T minus lambda times the identity map is a linear transformation on Rn, right? So we can write that in terms of its standard matrix, right? This is what? So like this is interchangeable with the standard matrix of T minus lambda times the identity map times V equals to 0, right? But how did the matrix of the linear transformation work? Remember how that works? It goes like, well, that's the matrix of T minus lambda times the matrix of the identity mapping all times V, which we could just as well write T minus lambda times the identity matrix times V is equal to 0. In other words, I have the following somewhat silly theorem. V is an eigenvector. I'm just going to say E vector for T going from Rn to Rn if and only if V is an eigenvector for the standard matrix of T, which of course is an n by n matrix, right? And just to be more clear, with the same eigenvalue, right? So what I'm trying to tell you guys is we do have choice. We can either talk about the eigenvectors and eigenvalues of a linear transformation, all right? Or we can talk about the eigenvectors and eigenvalues of a matrix. Now, for the most part, I'm going to make the focus in this class almost entirely about the matrix. But it is worth noting that the concept of eigenvector and eigenvalue really has its home with the concept of a linear transformation, and we'll see that more forcefully in the next course. All right? But anyway, let me take a step way outside of our context for just a second. I want to talk about the concept of an eigenvector in a more abstract sense, just for a minute or two with you guys. So, example 1, very abstract, all right? Although it's not too abstract. How about this? But we can think about, instead of looking at Rn, we can replace Rn with the set of like smooth functions. All right, the set of smooth functions form what's called a vector space, right? Like if you add two smooth functions together, you get a smooth function. If you take a scalar multiple of a smooth function, you get a smooth function. Now, at the moment, you're wondering what's a smooth function. The answer is It's a function that you can differentiate as many times as you like, and the derivative is always continuous. All right, so basically functions that are differentiable without end. So in this world, if we look at the transformation being, say, derivative with respect to x, right? And then I can look at, like, what does it mean for, t of v equal to lambda v? What's that mean? So that would be, dv dx is equal to lambda times v. See, that's a differential equation. Now, some of you had calculus too, yes? No? All of you? So you've studied differential equations. You know how to solve this, in fact, separation of variables, right? What is the solution? V is c1 e to the lambda x. So that means that any constant multiple of the of the exponential function e to the lambda x is in fact an eigenvector for the differentiation operator. Now, I'm using the word vector in a very abstract way at the moment, right? I don't mean a directed line segment, right? Whatever this word vector means, it's something much more abstract than that, yes? Because how many different functions are there like this? As many choices as lambda, you've got different functions. And you can prove that if lambda is not equal, like if I have lambda 1 and lambda 2 and they're not equal, e to the lambda 1 and e to the lambda 2 are linearly independent. So like exponentials with different arguments are in fact linearly independent functions. So there's infinitely many linearly independent eigenvectors for the differentiation operator. So we can't very well find a basis. By the way, this is an infinite dimensional vector space. I can't just list a basis of like n things, right? So that's why this is not part of this course in particular, because like we can't capture this structure with the simple finite matrix. It's something more than that, yeah? So that's one, just wanted to give you just a snapshot outside of the world of matrix linear algebra here for a second. In quantum mechanics, if you have what's called the momentum operator, all right, and you let the momentum operator act on the momentum eigenstate, you get P, bracket P. So here, this is a state vector, right? So the state vector is often labeled by the values that the eigenstates take with respect to the operator of interest. In this particular example, we're looking at a momentum eigenstate, right? The eigenvalue here is P. P is the value that P hat takes on cat P, as it's called, right? Again, this is very, very abstract. Depending on the kind of physical system you're working with, it could be a finite dimensional linear algebra thing, or sometimes quantum mechanics deals with infinite dimensional linear algebra. It just depends on the nature of the system. But anyway, so if you're interested in quantum mechanics, you need more than just the linear algebra in this course. You need to understand things that are a little bit deeper. Enough of that then. Just wanted to misbehave for a second here. So I think I've achieved that. Let's look at example 3. Back to Earth again. First a definition though. Let P be a n by n matrix with non-negative entries, so Pij greater than or equal to 0 for all ij, if the sum of entries in any column, I really prefer to say every column whoa, of P is 1, then P is a stochastic matrix. So here's a new kind of matrix we haven't talked about. All right, a stochastic matrix. So an example of this we could have P equal to first column 0.2, 0.8. All right. The next column 0.1, 0.9. So this would be a stochastic matrix, because 0.2 plus 0.8 is 1, and 0.1 plus 0.9 is 1. All right. Now, we're going to let x equal x sub k equal the number of, if my brain would work here, infected mice at beginning of kth week, and we'll let y sub k equal number of non-infected mice at start of kth week. Or if you like, you could say x is the number of sick mice and y is the number of healthy mice. All right. Then, like if we then say that x, x sub k plus 1, y sub k plus 1 is equal to this matrix 0.2, 0.8, 0.1, 0.9 times x sub k, y sub k, right? This is an example of like a stochastic process. Let me write down the formula here. So what we got is 0.2 xk plus 0.1 yk, 0.8 xk plus 0.9 yk. Now let's talk about what these formulas mean. Yeah? Let's put it in the words. So the first row there, it says that in the next week, how many sick mice do you have? You have so 20% of the mice that were sick in the previous week stay sick, right? And 10% of the non-infected mice get sick, right? On the flip side, 80% of the mice that were sick become well, and 90% of the non-infected mice stay non-infected, right? So this is the kind of thing a stochastic matrix can model. Is like you've got two populations, you've got some kind of rule that associates these two populations as time evolves, and we can set up a matrix multiplication to create what you might call a state machine, right? The state machine takes the kth state and creates the k plus 1th state, right? Yep.
I have a sinking feeling this is used in statistics a little bit.
Yeah, I mean, this is part of statistics, sure. Don't ask me about that, though. You don't like it either? Oh, well, this is harmless, though. So I'm going to call, let's just let big X equals to, xy, if that's okay. And so we're going to assume that the initial population is given by, for the sake of calculation here. We'll suppose that initially we have 100 mice infected to start. All right, and there's 1,000 total mice. So if there's 100 infected mice, how many did you got left? No, there's 1,000 total mice. If I got 100 infected, there must be 900 well, right? 900 healthy. All right, so that's our starting point. All right, start of week 1. So 1 week passes, we get to the start of week 2. Well, anyway, let me not enumerate the weeks. We'll just get confused. Anyway, so x1 is p times x naught. All right, but that's 0.2, 0.1, 0.8, 0.9 times 100, 900. What do we got? We got 20 plus 90, which is 110, right? We've got 80. Well, what's 1,000 minus 110? It's 890, right? Wait a minute. Is that right? Yeah. All right. Notice here that there's no. It's a very happy tale. No one dies, right? They just stay sick or they get well. There's no dying here, all right? So there's always the number of mice is conserved. It's always 1,000 as we go on. So there you go. That's x1. What's x2? It's p times x1, right? Which is what's that work out to? Well, I don't know, but I hope I have it written in my notes. So that, oh man, I called this, I'm sorry guys, I have to fix this, otherwise it can bother me. I called this x1, which I think would be correct with my, this is x1, so that makes this x2. I'm sorry guys, my numbering was off by a week there. I should have listened to my spider sense of tingling. Okay, so x1 is given, x2 we calculated, x3 ends up being 111,889. All right. So my question then is, what happens as k goes to infinity, right? In other words, if we take the limit as k goes to infinity of, x sub k, right? Which is the limit as k goes to infinity of what? What's the formula for x sub k in terms of p? Like another way to look at this would have been what? This is actually p squared times x1, right? We multiplied p twice to get this, right? So the kth one, I think, is p k minus 1. Oh, I'm a dummy. Well, that's true, but that's not helpful. What I really want to just say is this is p times, I'm sorry guys, I'll remember what I'm doing eventually here. P times xk minus 1. All right, this is true. Now, so the thing is, the limit is linear, so we can pull the matrix multiplication out front. All right? And so let's define the limit as k goes to infinity of x sub k. Let's call that x sub infinity, if you like, all right? And so what do we have here? We have that x infinity, right, is equal to p times what? Does it matter if you've got k minus 1 or k as you take the limit as k goes to infinity? No, it's the same thing, right? So we have x infinity times p times x infinity, right? And you guys tell me, what does that make x sub infinity? What kind of vector is it? What are we talking about today? Eigenvectors. This is an eigenvector of the stochastic matrix. What's its eigenvalue? No, P is the matrix. I see why you'd say that, but no. P is an eigenvector of the stochastic matrix P with eigenvalue lambda equals to what? Man, this thing is getting worse and worse. Every period it gets a little bit worse. I've now started having to pour the stuff into the. What's the eigenvalue?
1.
1. Very good. So every stochastic matrix, actually you can prove this. Every stochastic matrix has an eigenvector with eigenvalue 1, and that corresponds to, like, the steady state solution to the state machine. That's where everything gets drawn to eventually. It doesn't have to be just one. There could be multiple possible, like, steady state solutions, you know, for, and then it might depend on what your initial condition is, which one you get sucked into eventually, you know. But I believe you can prove that stochastic matrix has an eigenvector with eigenvalue 1. Once upon a time I assigned that as a homework in this course, but maybe not this course, maybe it's, so 1, yeah. All right, let's see if we can find the eigenvectors and eigenvalues for this particular matrix, right? Recall, we need the determinant of p minus lambda I equals to 0 for eigenvalues of p, right? But that's the determinant of 0.2 minus lambda, 0.1, 0.8, 0.9 minus lambda, like that, equals to 0. So I get lambda minus 0.2 times lambda minus 0.9 minus 0.08 equals to 0. All these decimals, I'm not enjoying them. Let's multiply this equation by 100. Multiply this by 100. What happens? I get 10 lambda minus 2 times 10 lambda minus 9 minus 8 equals to 0. All right, now I'm feeling better about my life. So now I multiply this out. I get myself 100 lambda squared minus, let's see here, 20 minus 110 lambda plus 18 minus 8, also known as?
Plus 10.
Thank you.
Should it be minus 20 minus 90? Going by 100? Like 100 lambda and 100 lambda? Yeah, you just know, because it's one term.
What they said. What they said. So, of course, at this point, I've grown tired of my multiplication by 100. I'm going to divide this by 10. So we've got 10 lambda squared minus 11 lambda plus 1 equal to 0, which I bet we could factor. 10 lambda times something equals to 0. Can we factor this? Of course, you could complete the square. Yeah?
I don't think everything is multiplied by 100 roughly.
Well, 100's 10 times 10, so I took 10 and multiplied it in here, and I took another 10 and multiplied it in there. So that's what I did. It seems to me that we're in business, we need a negative, right? How do you get a negative here? It's got to be a minus and a minus. How do you get minus? You get a 1. Okay, so if there's any hope for this working out nicely without the quadratic formula, it's got to be -1 and -1 here. Does that work? Well, -1 minus 10 is -11. Yay. 10 times 1 is 10. 10 lambda squared. Got the, yeah, we're good. All right, so my eigenvalues are, apparently, I've got lambda equal to 1, right? Or lambda 2 equal to, what is it? This is 0 when lambda is what? 1/10? Now let's find the eigenvectors. How do we do that? Let's see here. So the eigenvectors, we'll start with the lambda 1 equals to 1, 1. So we're looking for p minus the identity times, let's say, a vector, I'll call it u, equals to, I guess I should call it big X here, huh? But I usually do this. So I use u1, it's a 2 by 2, so let's see here. 0.2 minus 1 is minus 0.8. I've got 0.8 here. 0.1. 0.9 minus 1 is minus 0.1. And I usually use like a u and a v for my eigenvector just for the sake of calculation here. So what's the eigenvector? Remember we proved last time that they never come alone. They always come with, you know, there's always infinitely many solutions to the eigenvector problem. You can see that clearly that these two equations are the same equation, right? So going back to day 1, we're in that case where we don't have two equations, really, just got one, and so the solution set's infinite. I don't know, take whichever one you like. It's like 0.8u minus 0.1v is equal to 0, which shows me that v is equal to like 8u, right? Now this problem has a physical, well, okay, so to find x infinity, right? X infinity apparently has v equals to 8u, but there's something else for x infinity, right? If I set x infinity equal to uv, like I'm doing here, all right? Then of course that's what? That's, well, u is apparently, well, u is u, v is 8u, right? But what else do we know? We assume what? U plus v, which is in this case 9u, is equal to what? This is an assumption of the problem. Remember, the mice don't die. So the sum of the mice is 1,000. All right. Which leads us to the somewhat weird consequence that u has to be, 1,000 divided by 9. So my x infinity is ultimately, whatever that is. I'll find a decimal for you guys. So that's 111.111111111. And that gives us 888.88 continuing. There you go. That's the eventual state of this sick, healthy mouse problem. Now, at this point, you run into other questions, right? Like, how do you have 0.11111 repeating mouses, right? I guess this means in the end, there's one mouse that's like 11% sick and 88.88 repeating well, if you want to look at it that way. I don't know. These problems break down if you think about them too hard, because, you know, taking the limit, it's just giving us a qualitative description of what's going on, right? Okay, so, but anyway, you can already see that happening, right? And it's getting, I started at 100, I'm up to 110, now I'm at 111, and if we kept doing this, we just keep homing in closer and closer to 111.1111. It just continues. And if I had started further away from the answer than this, if I'd started with like, I really should have started with like half and half, sick and well, and it would have taken a few more steps for us to get closer to the limiting one. Okay, so this is one of the reasons that you'd be interested in eigenvectors, is because they have significance for stochastic matrices. They're apparently eigenvector with eigenvalue 1 is the steady state solution to the state problem, right? Okay, so how about the other eigenvector? Lambda 2 equal to 0.1. So we're looking at P minus 0.1 times the identity matrix times U2 equals to 0. So that is, let's see here, 0.1, 0.8, 0.1, 0.8 UV. So I use the U and the V as like disposable variables here, guys. All right. If you don't mind, I'm going to erase my characteristic equation so I can work over here. All right, so we got, well, I mean, what's there to do? What's this tell us? There's one equation, right? It's 0.1u plus 0.1v equals to 0. Or if you like, 0.8u plus 0.8v equals to 0. So apparently v is equal to minus u. And so what can we say about this? I mean, we could write down the eigenvector mathematically. And mathematically, basically, you've got, you know, u minus u, which is something of the form u times 1 minus 1, right? So this is your, you know, typical eigenvector with eigenvalue lambda equals to 1/10, right? But this problem has a physical origin, and my question to you is this solution physically realized by this state state machine? I think not, right? Because what would we mean by negative population? You're like, you have some friends like that, it makes sense to you. I mean, I get that, but, no, I think negative population means that this is not a physically interesting solution, as far as I could think of anyway. So, but nevertheless, that is an eigenvector for that matrix, all right? Okay, let us go on. Let me take a break from my example stuff and give you a theoretical result. Theorem. T is diagonalizable. All right, meaning that the matrix of T with respect to some basis is equal to a diagonal matrix. right? Which means this, right? So T is diagonalizable if and only if, well, let me just use the double arrow. If and only if there exists an eigenbasis. And what does eigenbasis mean? That is a basis of eigenvectors for T. So we last class I gave you an example where we saw a linear transformation on R3, and we saw that there's a particular basis that diagonalized that transformation, and that was an eigenbasis. So that's an example of this theorem. So what is the matrix of T with respect to a basis? Remember what this means is T of V1, T of V2, T of Vn. Right? This is basically our definition of the matrix of a linear transformation with respect to a basis beta. What's beta? I'm saying beta is V1, V2, Vn, all right? All right, so let's think about, I'm going to use two different colors. So I'm going to first of all think about the forward implication, all right? The forward implication, I'm assuming that T is diagonalized with respect to the basis beta, right? That means that this matrix actually is what? It's like basically D1E1, D2E2, DNEN. That's what this is, okay? But what that means then is that, the coordinate vector of the jth vector in the basis with respect to the coordinate system is equal to dj times ej. But what that means, right, is that T of Vj is equal to dj times Vj. What does that make the jth standard basis then? It's a what? It's an eigenvector for T with eigenvalue what? DJ, right. So Vj is eigenvector with eigenvalue d sub j. All right. And that proves the forward implication of the theorem, namely that if T is diagonalizable, then it has an eigenbasis, because the basis which diagonalizes it is the eigenbasis. Now the other direction, if I dare. So we're going to assume that T of Vj is equal to lambda j Vj for all j ranging from 1 to n. Then the matrix of T with respect to the beta basis is literally like, okay, so like my T of V1 is lambda 1 V1. Calculate the coordinate vector of that. And then I've got lambda 2 V2, calculate the coordinate vector of that. Lambda n Vn, calculate the coordinate vector of that with respect to this basis. again, I'm assuming I have an eigenbasis. Well, look, this, by definition of the coordinate map, is lambda 1 E1. And then you got lambda 2 E2. Lambda n En. Now, if you don't follow my arguments, it's okay. It just means that you're not as comfortable as you need to be with the coordinate map idea. Once you understand that completely, this proof becomes stupid. If you're confused right now, it's probably that you don't entirely understand how the coordinate map is defined. And that's okay for this class. But anyway, this is exactly lambda 1, lambda 2, lambda n, right? Which is a diagonal matrix with the eigenvalues down the diagonal. So actually the theorem is a little bit stronger than what I've said. It's not just that the linear transformation can be diagonalized if it has an eigenbasis, and only when it has an eigenbasis. It's that a linear transformation is diagonalizable if and only if it has an eigenbasis, and the values on the diagonal are exactly those eigenvalues. So that's the thing. All right, let me move on here. So I have to be careful in here because the examples in this class can like eat up oodles of time. I should probably speed them up a bit. So here's a theorem, or rather a proposition that we should meditate on for a second here. Proposition: the following are equivalent for A in Rn by n and lambda in the complexes. So number one, lambda is an eigenvalue of A. 2, there exists v not equal to 0 such that AV equals to lambda v. 3, there exists v not equal to 0 such that A minus lambda I times v is equal to 0. Number 4, lambda is solution to the determinant of A minus lambda I is equal to 0. And number 5, A minus lambda I times v equals to 0 has infinitely many solutions. Now, admittedly here, guys, I'm taking some liberties with the definition that I gave you already. I think when I wrote the definition for eigenvector here, I assumed that the eigenvalue lambda was what? I think I said it had to be real, didn't I? So this proposition is extending the concept of eigenvector for A to allow the possibility that the eigenvalue be complex. Now, technically speaking, some people would say that's not an eigenvalue. All right, some people would say if lambda is complex, it's not really an eigenvalue because if you got a real matrix, the eigenvalue has to be real. Okay, so probably I should say something along the lines of remark we say lambda equals to alpha plus I beta with beta not equal to 0 is a complex eigenvalue. All right. With that slight modification of the language, I think the proposition's okay. It's just we're going to say we have eigenvalues which are genuine eigenvalues. Those have to be real. But we also have complex eigenvalues, right? And to be fussy, the complex eigenvalues technically belong to what I would call the complexification of the map. But listen, the way we calculate the complex eigenvalues is just the same as the way we calculate the eigenvalues. All right? Like, for example, what am I on example 4? I can't remember. So do you guys know the formula for like a rotation in 3 dimensions around the z-axis? So we could do this. T of x, y, z equals to, we do like cosine theta, sine theta, maybe minus sine theta up here, cosine theta here, 0, 0, put a 1 here. So what this does, right, is it, if here's your input, let me put my input over here. All right. And this angle is theta. And over here is your t of v. All right. So like this is a rotation around the z-axis. That's what this formula is.
Theta a constant here?
What's that?
Is theta a constant here?
Yeah, theta is a constant. Yeah, yeah. So in fact, let's be more boring. Let's make theta equal to, what do you guys want? Like pi over, want to put theta equal to like pi over 6 or something? So then cosine of theta is what? Like root 3 over 2. And sine theta is what? Yeah, 1/2, yeah. Okay, so what is the determinant of t minus lambda equal to? Well, we're looking at the determinant of, you know, root 3 over 2 minus lambda 1/2, minus 1/2 rather. 1/2 root 3 over 2 minus lambda. Let me put some dividers in here. 0, 0, 0, 0, 1 minus lambda, right? So, okay, great. This gives us lambda minus root 3 over 2 quantity squared plus 1/2 squared all times 1 minus lambda. So this transformation has one real eigenvalue. The real eigenvalue is what? One, right? And also we have lambda, you know, let's say lambda 2 and 3, or if you like lambda plus and minus, what I usually do, equals to root 3 over 2 plus or minus, you know, I over 2. This is a pair of complex eigenvalues. So they have to come in a conjugate pair. That's the way this works, right? Can you guys tell me what is the eigenvector with eigenvalue 1? You can guess it without calculation here. How about 0, 0, 1. Look at that. Multiply the matrix by 0, 0, 1. What do you get? 0, 0, 1. Now, how did I know this was an eigenvector with eigenvalue 1, besides the fact I've worked this problem half a dozen times in my adult life? Setting that aside. It's a rotation, right? What vector is fixed in a rotation? In 3 dimensions. There's a rotation axis, right? The rotation axis must be an eigenvector with eigenvalue 1, because it's fixed under the transformation, right? The axis doesn't, I mean, you can't rotate the axis like, you know, it's still the z vector, z hat vector if you like, or k if you use that notation. So there you go, that is the eigenvector with eigenvalue 1, and that's the only real eigenvector here, right? Actually, the other eigenvectors for this matrix would be complex, all right? And we'll work those out another day. I don't want to do the complex eigenvectors today. But you need to be aware that they're there. So this transformation is an example of a matrix which is not diagonalizable. All right, because the vectors that you'd like to be eigenvectors, they're complex eigenvectors. You can't find 3 real eigenvectors here. You can't find an eigenbasis in the real sense for this matrix. Now you can diagonalize this matrix with respect to complex numbers. So this matrix is what is an example of a complex diagonalizable matrix. So it can be diagonalized over the complex numbers, cannot be diagonalized over the real numbers. But this right here, this list, is just a litany of all the different ways we can look at the matrix A minus lambda I not being invertible, right? These are all equivalent conditions. Yes, sir?
Maybe slightly unrelated, but what's the physical significance of having a complex value where the real e value is just the vector that you're rotating about? You know, what physical significance to the other?
Well, I mean, the presence, pretty much exactly what this example is. Like the presence of a complex eigenvalue means that there's a choice of basis, which the transformation becomes a rotation / possibly rescaling with respect to that part of the basis. So like eigenvectors, on the other hand, so what happens along an eigenvector direction, generally speaking, is just that the linear transformation rescales. If the eigenvector is bigger than 1, it takes vectors along the eigendirection and like makes them bigger. If the eigenvector is smaller than 1, it shrinks vectors along the eigendirection, right? But with a complex eigenvalue, it's not a shrinking. Well, it can also be a shrinking or a stretching, but it's a shrinking or a stretching with respect to some plane and a rotation around the axis of that plane is what it means. And that's already present in this example. The plane in question here I'm talking about is the xy plane. So like the complex eigenvectors are going to have they're going to have no z component, and they're actually going to have an x and a y component in this problem. But anyway, let me show you guys some more examples. We should work some 3x3 examples. I say plural, but probably I only have time for, like one here at the moment. So, example 5. Suppose we have A equal to 0, 0, minus 4, 2, 4, 2, 2, 0, 6. All right. So what we're going to do in here is I'm going to work this problem relatively slowly. But at some point, I'm going to get the projector out, and we're just going to go through a bunch of examples all at once. Because I simply do not have time to work out all of the possible flavor choices at this level of material compression. But I think it's important for you to see me work these problems relatively slowly so that you understand the mechanics of it, right? So we want to find the eigenvalues and eigenvectors for this